Good afternoon. How many of you all here have heard about the new discovery of gravitational waves and the LIGO experiment? Alright. What I'm trying to explain here is the background of how gravitational waves work. When I say the word Albert Einstein, what is the first thing that comes to your mind? Anybody loudly? Science. Okay. Apple was Isaac Newton. See, here. Any equations, anything that he... What we do normally forget or we do normally ignore are many other powerful ideas that this man has given to science. Some of them are his theories of relativity. If I am standing outside a platform and I have a train running in front of me, people inside the train for me are in motion. But for the people inside the train, other people inside the train are stationary. This is relativity. Now, somebody talked about the apple. Apple falling on the earth is normally what we call gravity. You standing here and not floating in the air is what we call gravity. This was given by Isaac Newton. He said that when any two objects are present, they attract each other by some mystical force, as he called it. He could not explain how. He could not explain a field. He could not explain any basis for the two objects to attract each other. So Einstein proposed his theory of relativity and he tried to explain how gravitation can work. Now, Einstein did not disprove Newton, no he did not. He just gave a basis for Newton's theory of gravitation to act. As you can see, Einstein's equation used capital G, which is the universal constant of gravity that was derived by Newton. Einstein, a very smart guy, he said space and time, that is space, that is where we are, and time, when we are there. Space for us right now is the conference room, here. And time right now is 12:40. He said space and time are not two very different things. He said space and time are interwoven. They are part of the same entity called space-time. Space-time can be thought of as a graph paper on a trampoline sheet. How many of you all know what a trampoline is? A trampoline. Alright. So, instead of having a stretched rubber sheet on the trampoline, you have a graph paper. As you might expect, when you stand on the trampoline, you curve the trampoline downwards and hence the graph downwards. Heavier you are, the more you will bend the trampoline downwards, as is seen in the picture. This bending of the trampoline graph that I just talked about is called warped space. Warped meaning curvature. This was observed when we tried to locate the position of stars in the galaxy. As you can see, light from the star gets curved around the trampoline surface around the sun. And we think that the star is positioned somewhere else. I talked about warped space, now let me talk about warped time. How many of you all here have used maps in your phones or in your parents' phone to get to places, to navigate to places? So that works on the global positioning system, the GPS, which has satellites up in space. Now, like in the example of the trampoline on the surface of your foot is curved more than it is on the outside. Hence, time on the outside moves faster than it does on your surface. Compare that to the entire GPS example. Time in the global positioning satellite moves faster than it does on the Earth's surface. The difference being 40 microseconds. Now you might say 40 microseconds is not a big deal, but it actually is. 40 microseconds accounts for a distance of 10 kilometers on the Earth's surface. Imagine if your GPS was working 10 kilometers before you. It would be a big problem. Alright, so this is the basis of what space-time as a trampoline is. Now, to step up the fun, what if the object you place on the trampoline is so heavy that it curves the trampoline so much that even light cannot escape from it? You just got yourself a black hole. This is not an actual image, it is a computer simulation of a black hole. To tell you how massively dense black holes are, if the entire mass of the Earth were to become a black hole, it would be the size of a table tennis ball. That's how massively dense black holes are. To double the fun, what if you have two such black holes? This is called a binary black hole system, where binary stands for 2. Such systems do exist but are very difficult to capture. And when they do exist, they dance a very delicate dance about themselves. They orbit around each other and they get closer and closer and closer. Their speed increases, and close to the speed of light, they merge. And a massive explosion releases energy that can light the galaxy for one instant. Now, since I was talking about that trampoline and the graph, I will show you what happens to that graph when two such black holes collide. Notice how they get faster when they get close to each other. And also, if you notice at the edges of the screen, there are these waves that are produced in the graph. These waves are what we call gravitational waves. If you have an electron and you move it, it produces an electric field. Similarly, if you have a mass and you move it, it produces gravitational fields in space-time. Now, gravitation is the weakest of any force in the universe. And even when two black holes collide in a high energy explosion, the waves produced are of very small energy. To detect them, we need very, very, very sophisticated instruments. And there comes in LIGO. Laser Interferometer Gravitational Wave Observatory. The instrument is as complex as the name is, but we do have a very simple version showing the principle of how this works in the first floor demonstration lab. So the LIGO works at a vacuum which is the smallest vacuum that there is on the planet, and maintaining that is a lot of effort. But we have confirmed the theory that I just talked about, and we have confirmed that Albert Einstein was right 100 years before. We stand at a point where technology and advances are in the frontier. We will discover new discoveries, we will find new happenings. All we need to do is keep our eyes open and stay curious. Thank you.